Hey there! Welcome back to some more awesome sauce series convergence and divergence tests. In this lesson, we're going to go over the ratio and root tests. Specifically in this one video, we're going to hit up the ratio test, all the conditions that go with it, how to use it, and why it works. So let's jump into it. So the ratio test has three separate paths that we could go on, and they're actually relatively simple, but it's pretty algebraic. We'll see that in a little bit. So the ratio test says that if you've got some series from n equals 1 to infinity or n equals 0 or any value there of some sequence, it will converge. So that series will converge absolutely, meaning not just conditionally, but absolutely. So you can use this on alternating series as well. It will converge absolutely if the limit as n goes to infinity of the n plus first term over the nth term, the absolute value of that, is less than 1. Essentially what you're doing is you're basically saying, let's go way, way, way out in this series and make it into like a geometric series. Get a ratio of the next term divided by one term before it. And if that ratio acts like a converging geometric series, that is less than 1, that common ratio, then we're going to converge. We will diverge if the limit as n goes to infinity of that same absolute value of that ratio test, is greater than 1. Unfortunately, the test will fail if the limit as n goes to infinity of the absolute value of that ratio is equal to 1. So this means that we must use a different test. So what that means is we must have picked a test, that ratio test, incorrectly there. So when do we pick the ratio series test? Well, we pick that when a series contains fast functions or messes. So like lots of factorials and exponential functions, the ratio test is great for that. If you have things like n squared, n cubed, p-series type things, square roots, things that are not so fast, then the ratio test is not going to work. It'll fail. We'll get it equal to 1, and we should use another test for convergence. So as I said, think exponential and like factorial functions. Okay, without any further ado, let's put this awesome, awesome test to work. State whether the series converges or diverges, justify your answer. So as usual, when we justify our answer, we're going to state the test we're using, show the conditions of the test, and then state our conclusion in any order. So first thing I notice here, if this is a multiple choice question, I've got 4 to the n over n factorial, and n factorial is so much faster than 4 to the n. You can look at that actually in 9.1, right? Chapter 9, lesson 1 videos where I go over the comparison of exponentials and factorials. So we can be pretty certain that this thing is going to converge. But we'll use the ratio test on it. You can expand it out if you want, but you don't have to. I'm not going to here. I notice it's pretty fast, not messy, but very fast functions. So I'm going to take the limit as n goes to infinity of the n plus first term divided by the nth term, right? And that's the absolute value of that. And so that's equal to the limit as n goes to infinity of, so what's the n plus first term here? That's literally plugging in n plus 1 for each of these values. So that would be 4 to the n plus 1 all over n plus 1 factorial. That right there is your a sub n plus 1 divided by, oh my goodness, it's going to be divided by this term, the nth term, which is the exact value that you have in your series. That's 4 to the n over n factorial. Okay, so now the rest of what we have here is algebra. So these are the conditions that we're showing. Not a lot of words in the ratio test. So if you like algebra, this test is for you. So the limit as n goes to infinity, the absolute value of, we'll have 4 to the n plus 1 all over n plus 1 factorial. And what I'm going to do here is recognize that I'm dividing by a fraction. So that's the same as multiplying by the reciprocal. So in the next example or two in this video, I'm going to just go right to this step right here. And we understand that dividing a fraction by a fraction is multiplying by the reciprocal. Now, we're going to do some simplifying before we take our limit. N factorial and n plus 1 factorial. Well, remember, n plus 1 factorial, I'll write in a different color here, is n plus 1 times n factorial. Go back to my review of factorials in lesson 1 in this chapter so that you understand how to simplify this down. That's why I went over it. It's for this very idea right here. So the n factorials will divide out. That's nice. 4 to the n plus 1 and 4 to the n, you essentially have 4 times 4 to the n. There's one more factor of 4 in the numerator than the denominator, so the 4 to the n's will divide out, leaving you with just a 1 up top from the n factorial canceling, a 4, and then n plus 1. It's actually a pretty easy limit to then take. you'll see in a second, we get the limit as n goes to infinity of 4 all over n plus 1. I'm going to take away the absolute value because there's nothing negative in here. We're going to positive infinity. And 4 over positive infinity essentially is what you're looking at in your brain is equal to 0, which is less than 1. So then I can say by the ratio test, our series converges. That's it. So where's my condition then? My condition is actually in my work. I've shown that the limit of the n plus first term divided by the nth term, the absolute value of that, goes to infinity and then ends up equaling out to 0. That limit as we go to infinity goes to 0, which is less than 1. That's an important part right there. Got to state that it's less than 1. You're showing you understand what that ratio has to be less than. So by the ratio test, our series converges. It's nice. All right, let's look at another one. So here we've got our real messy expression. I'm not going to expand that thing out, but it's messy. We've got exponentials involved. We've got some alternation. This is one for your ratio test. So we'll take the limit as n goes to infinity and beyond of the absolute value of the n plus first term. So you'd be plugging in n plus 1 into every single n value there. So that's times n plus 1. Oh, what a mess this is going to be. Times 2 to the, we're doing n plus 1 minus 1 right here. The minus 1's cancel and you're left with just 2 to the n then, all over 5 to the, now we're plugging in n plus 1 into this, and n plus 1 minus 2, plugging in n plus 1 minus 2 is n minus 1. Now, as I did in the last problem, I'm going to multiply by the reciprocal. That's the same as dividing by the nth term. So the reciprocal would be just everything you see here flipped. A lot of copying. Don't be scared by the nastiness. We're going to go piece by piece and break this thing down. All I'm doing is copying the exact nth term, but it's reciprocal. So be careful to make sure you copy everything correctly. All right, now before we take a limit, we're going to just whittle things down. Now, first of all, the absolute value is going to completely take care of the negative numbers. The negative 1 will become 1, right? Both of those. The absolute value of negative 1 is 1. Now, from here, what we should notice is we've got a couple things that we can simplify. You've got n minus 2 5s and n minus 1 5s. That's one more 5 down here than you have up there. So these will all divide out, leaving you with one more 5 down in the denominator. And maybe I'll do that in a different color, just so that that sticks out. So we got one more 5 left down there. We can do the same with a 2 to the n. You have one more 2 to the n in the numerator than you do in the denominator. So 2 to the n minus 1 will cancel with 2 to the n, leaving you with just 2. Let's simplify this down a bit. Limit as n goes to infinity of the absolute value of, now we still have an n plus 1 over that n. Don't let those things hide out there. You have a 2 up top, right there, and nothing else up top. Everything else is 1s, and then a 5. Now the reason why I'm going to just separate off that 2/5 right there is because I'm really only focusing my limit on the n values, right? And then multiplying that result by 2/5. Well, the limit as n goes to infinity of n plus 1 over n goes to 1, right? So that's going to end up equaling to 1 times the 2/5, which is less than 1. And so our series, the series converges by the ratio test. So series converges by the ratio test. Isn't that beautiful? Well, I think so too. So that's it. So that's converging by the ratio test. Slightly different, more messy function, but not so bad. All right, let's take a look at this one right here. See if it converges, diverges, or maybe we don't have enough to make a justification. Let's see. So we'll take the limit again as n goes to infinity of the absolute value of the n plus first term will be negative 1 to the n plus 1 times n plus 1, just plugging in n plus 1s everywhere, all over n plus 1 squared plus 1. All right, so now looking at this, what we've got going on is we've got our n plus first term. We're going to multiply that now by our nth term, the reciprocal of it. So that's going to be n squared plus 1 all over negative 1 to the n times n. Now you might notice right from the get-go that this is a fairly simple alternating series. So I mention that because since it's an alternating series, and it's not that fast, like there's no exponentials or factorials, the ratio test might not be the way to go, and that's pretty much the lesson here. So we're going to simplify this down. The negative ones get completely clobbered by the absolute values, right? And what you're left with is the limit as n goes to infinity of, and essentially we don't need the absolute values because we're going to a positive number and everything else is positive, n plus 1 times n squared plus 1 all over n times n plus 1 squared plus 1. And you might be looking at that like, all right, what's that limit? Here's the thing. This is basically the limit as n goes to infinity of the highest powers in the numerator and denominator, which is the limit as n goes to infinity of n cubed. That's the highest power down here. And then down here too, n squared times n is n cubed, which is equal to 1. That's equal to 1. Therefore, the test fails. We use the wrong test. So what's the right test here? Well, the right test would be the alternating series test. What you can see is when we expand this thing out, let's expand that thing out right there. So I'm just going to draw an arrow. We'll expand it out. The first term when I plug in 1 is going to be negative 1. So it's going to be a negative 1 all over 1 squared plus 1 is going to be 2. And then we're going to go to plus when we plug in the 2, we're just going up by 1's up there, over 5 minus, we plug in 3. You're going to get 3 over 10 plus, and then we're going to go 4 all over 17 minus, and then it just keeps on going on and on like that until you get out to the nth term, negative 1 n times, let's see, n all over n squared plus 1. And it keeps on going on and on and on. Now, here's the thing. The terms decrease in absolute value to 0. Therefore, the series converges by the alternating series test. So I'll say since this alternating series terms decrease in absolute, I'm doing a lot of abbreviations here, in absolute value to 0, the series converges. That's it. So we did not use the proper test when we used the ratio test. So I wanted to show you what to do when that happens. Well, what to do? You use a different convergence test. All right, we got one more thing in store here as this video goes a little bit longer, but that's okay. Ratio test is important. It's all one lesson bundled into one. The question is, why does the ratio test make sense? Here's why all those conditions make sense. You're basically expanding out a series like this. A1, A2, A3, A4, adding them up until you get to an plus 1. And we're saying if it acts like a geoseries, like a converging geometric series, and I'll write that down, acts like a converging geometric series, then it converges. That's essentially what the proof behind this shows. And I'm not going to go over a proof here. So in this case, you're basically geometrizing the series. You're saying as n goes to infinity, if we take the absolute value of the ratio of every succeeding term divided by the preceding term, does that end up being less than 1? And if it does, then we converge. If it acts like a diverging geoseries, then our series diverges. Oh yes. Oh yes. Why is that? Well, again, you're looking out to the nth term and you're saying, well, let me take the n plus first term, the very next term, every time, divided by the preceding term. By doing that, you're getting like a common ratio as we go out to infinity, and you're saying, oh, if that's greater than 1, then we diverge. Now, if it's equal to 1, the reason why this thing fails is because there are some series that, when you use the ratio test that equal to 1, converge. That's like the one we just looked at a little while ago, the alternating series. And there's others, like the harmonic series. If you were to use it with, it would equal to 1, but that one diverges. So because we have that counterexample there, equal to 1 is never conclusive. All right, awesome video. I had a great time. Hope you did too. The sun came out behind me while we were making it. I guess it's over this shoulder. That was pretty sweet. I'll see you in the next one. Root test. Peace.